Welcome to our very last unit. Unit 8 is on solving quadratics. Before we do any work on solving quadratics, let's first talk about what quadratics are. So an introduction. A quadratic equation is any equation that fits the form ax squared plus bx plus c is equal to 0. In that form, a cannot be 0. So we've seen this form before when we talked about factoring trinomials and we identified the a, the b, and the c. This is the standard form of a quadratic equation. And in this form, the value of a cannot be 0. But the value of b could be 0, and the value of c could be 0. If b was 0, then our equation would look like ax squared plus c equals 0. If c was 0, then our equation would look like ax squared plus bx equals 0. The reason that a cannot be 0 is because the x squared term is what makes something a quadratic. We'll talk about that in just a second. As I mentioned just a second ago, this form is called standard form of a quadratic equation. So when we talked about linear functions previously, linear function had a standard form, and so do quadratics. So this ax squared plus bx plus c equals 0 is standard form. All of our terms are on the left-hand side, and we are equal to 0 on the right-hand side. I guess I should say all of our terms are on the same side, and we are equal to 0 on the other side. The degree of a quadratic equation is 2. Right? So we've talked previously about linear functions, and in a linear function, the largest exponent that we would see in the problem was a 1. In a quadratic function, the largest exponent that we are going to see in the problem is a 2. So we say the degree of a quadratic is 2, and that means that after the equation is completely simplified, then the largest exponent we see in the problem is going to be a 2. So that squared right there is very, very important in making this a quadratic function. And that is why we say that a cannot be 0. Because if a was 0, this ax squared term would be gone, and we would be left with bx plus c, which is actually a linear function. Okay. The graph of a quadratic equation is no longer a straight line like we studied with linear functions. The graph of a quadratic equation is a U-shaped curve. Right? That U-shaped curve can open upward and look like this, or the U-shaped curve can open downward and look like this. Right? Either way, that U-shaped curve is going to be called a parabola. P-A-R-A-B-O-L-A. Parabola. All right, let's talk a little bit more about a parabola. So one thing that a parabola has, it has a special property. Okay, I can take any parabola, again, whether it opens upward or downward, and I can fold the parabola so that the two sides match exactly. So I can take this arrow here on the right, and I can fold it over to match the arrow there on the left. Okay, and I create two halves to my parabola there. Same thing with the one down here. I can fold the arrow here on the right and lay it on top of the arrow there on the left, and it creates this line down the middle of my parabola that creates two halves. Okay? This property, where we have this line down the middle that creates two sides that match exactly, is called symmetry. So that fold that I made in my paper, or that line that divided the parabola into two matching halves. Okay, so this purple line that I drew right here and right here, that line is called the axis, A-X-I-S, of symmetry. Okay, some books refer to it as a line of symmetry. Okay, so that purple line that divides the parabola into two equal halves is called the axis of symmetry. Notice that that purple line, or that axis of symmetry, is a vertical line. Okay, notice that whether the parabola opened up or whether it opened downward, that line was a vertical line. Right? Because of this, the equation for the axis of symmetry will always fit the same form. So if you remember back to Unit 5 when we talked about linear equations either have an x and a y in them, or just an x or just a y. And so if our line was a vertical line, then during that unit we talked about how vertical lines only touch the x-axis. And therefore, when we go to write the equation for the axis of symmetry, it is always going to be x equals, and then whatever number our line goes through on the x-axis was what we would set this equal to. Okay. All right. One other key property of a parabola is a point called the vertex. The vertex, as I mentioned, is a point, and it is either the highest point or the lowest point on the graph, okay, of a parabola. So it is the highest or lowest point on a parabola. So in this case, we can see right here, the highest point on this graph is located right there. So that is my vertex. And on the graph that opens upward, I have a lowest point that is located right there. That is my vertex. Notice that in both cases, the vertex was on both the parabola, but the vertex also lies on the purple line, which was called the axis of symmetry. So the vertex will always lie on the axis of symmetry. Last two vocabulary words. Finally, if the vertex is the highest point on your graph, or highest point on the parabola, then we call that the maximum. So another name for the vertex could be the word maximum if it's the highest point. In this case, this vertex is a maximum because it's the highest point on the graph. If the vertex is the lowest point on our graph, then we call that point the minimum. Right? So in the picture where the graph opens up, this isn't just the vertex, it is also a minimum. All right, that takes care of all of the vocabulary that we want to talk about as we introduce quadratics, right? So getting the big idea that we are no longer talking about straight lines, we are now wanting to talk about curved lines, okay? Quadratics are curved lines that graph as a U shape that we call a parabola. What makes it a quadratic is that we have the squared term in our problem, and that squared term is the largest exponent that we see in the problem. All right, the last thing we want to talk about today is the zero product property. And zero product property is going to be used in our next lesson on solving by factoring. So today we just want to get an idea of what the zero product property is and how it could help us. So the zero product property states that if A times B is equal to 0. So in other words, if I have a product, multiplication, and my result is 0, what do I know about my numbers? Well, If I think about two numbers that multiply together to get 0, my example would be something like 5 times 0. Okay, that might not have been the example that you thought of. 3 times 0 will also make 0. Finally, 0 times 6 is also 0. What we should see is that if we have a product that is equal to 0, then one of the numbers in the product had to be 0. So either this number here in the first position, which we are calling A, had to be 0, or the number here in the second position had to be 0 in order for the product to be 0. Okay? So again, all it's saying is that if we're multiplying two things together and the answer is 0, then one of the things that we multiplied had to be 0, right? So if A times B is 0, then either A was 0 or B had to be 0. Okay? Okay, again, this means that if two numbers, terms, or expressions are multiplied together and their product is 0, then one of those numbers, terms, or expressions must be equal to 0. So, how does this work with what we're talking about? We've been talking about factoring. In this example, if x plus 3 times x minus 7 is equal to 0, then I know that one of these things, either x plus 3 or x minus 7, had to have a value of 0. Okay? So what I can say is if x plus 3 times x minus 7 equals 0, then x plus 3 was equal to 0. Okay, so I would have a 0 here. So 0 times x minus 7 would be 0. Or x minus 7 needed to be 0 because x plus 3 times 0 would make 0. Okay. In the second example, if we know that 2x minus 1 times x plus 5 is equal to 0, then either this part of the expression or this part had to be equal to 0. Okay? If a product is equal to 0, then one of the factors had to be 0, one of the things we were multiplying. So what we can say here is that if 2x minus 1 times x plus 5 equals 0, then 2x minus 1 is equal to 0, because 0 times x plus 5 would be 0, or x plus 5 had to be 0. 2x minus 1 times 0 would be 0. All right, on the last one, we have two factors there. We have a factor of x, and it is multiplying 2x minus 9. If x times 2x minus 9 equals 0, then we can say x equals 0 or 2x minus 9 equals 0. Okay. So how can the zero product property help us? Well, what we can do now is apply the zero product property and figure out the value of x. Right? So here, if x plus 3 was equal to 0, then I know that x would need to be negative 3. Subtracting the 3 over, x equals negative 3. And I can show you, if x is negative 3, then negative 3 plus 3 would make 0. Negative 3 minus 7 would make negative 10. 0 times negative 10 would be 0. Okay? So we want to apply the zero product property to each of these four examples to help us solve for x. Right? So here we've got a product, x plus 2 times x minus 1, and I see that that product is equal to 0. According to the zero product property, either this x plus 2 was equal to 0. Oops. Sorry about that. X plus 2 is equal to 0. Or we know that x minus 1 is equal to 0. Can't write today. All right, knowing that, we now have two smaller linear problems that we can come through and solve. If I solve this, I'll subtract 2 on both sides. In order for x plus 2 to be 0, x would need to be negative 2. And in order for x minus 1 to be 0, x would need to be positive 1. So we have now found the value of x. Right? These are the solutions. So these are the only two numbers that I could plug in here that would make this equation become true. Right? Plugging in here, -2 plus 2 makes 0. And -2 minus 1 makes -3. 0 times -3 would make 0. Likewise, if x was 1, then x plus 2 makes 3, and 1 minus 1 makes 0. 3 times 0 will also make 0. Right? We can write our answer as a solution set. One value for x was -2. The other value for x was +1. In the second example, x plus 5 times 2x minus 3 equals 0. We have a product that is equal to 0, so we can apply our zero product property. Either x plus 5 is equal to 0 or 2x minus 3 is equal to 0. Solving each of these, I can subtract 5 here to figure out that x would need to be -5. I can add 3 and divide by 2 here and find that x would be 3/2. Again, I could plug each of those in and see that they do make the equation true. Therefore, my solution set would say that x can be -5 or x could be 3/2. In our final two examples, 6x plus 7 times 4x minus 11 is equal to 0. Taking a look at that, I can see that I have a product that is equal to 0. So either 6x plus 7 is equal to 0 or 4x minus 11 is equal to 0. Solving each of these, on the left-hand side, if I subtract 7, I get 6x equals -7. And when I divide by 6, I find that x would need to be 7/6 for that to become 0. On this side, we would add 11. 4x is equal to 11, and so x is equal to 11/4. So x would need to be 11/4 as our other answer that would make this equation true. Right? So my solution set would say -7/6 or +11/4 would both make my equation true. Right? And for our last one, again, I have a product, -3x times 2x minus 5 is equal to 0. So if I apply the zero product property, one of my factors was -3x. The other factor or thing I am multiplying is 2x minus 5. So each of those would be 0. And when we solve here, we would divide by -3 to find that x is 0. And if we solve here, we would add 5 and divide by 2. And we would find that x is equal to 5/2. So our solution set would say one value that makes the equation true is 0. The other value that makes the equation true is 5/2. All right, you try question 5 and 6 and then check your answers. Question number 5, your two solutions should have been -4 and -3. And on question number 6, your solution should have been 0 and +3/2.